Lesson 13 is called Theorems about Tangents, and remember, tangent lines are lines that touch a circle at like exactly one point, but they don't cross into the circle. So 13.1, we're going to start up at the top. So the first theorem, if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. So if we look at the graphic on the right, the line AB is tangent to that circle C, and because it's tangent to it, the radius, like CD, this section, is perpendicular to that tangent line because that radius is drawn to that point in tangency D. And then the second theorem is just the converse of that original one, which is just kind of like the reverse of it. So if a line is perpendicular to the radius of a circle at a point on the circle, then the line is tangent to the circle. So like we have in this case, we maybe wouldn't know or be given that we have a tangent line, but if we do know that it happens to be perpendicular to the radius, then it must also be tangent. Okay, example 1, determine whether segment AB is tangent to circle C. So in this case, we don't know for sure if segment AB is tangent. We're trying to prove that. So actually I'm going to zoom out so we can see those two theorems. So the one at the top is more of like if we know it's tangent. Like we've already known it, we've already confirmed it. If we confirm it, then we can kind of go on to say that it would be perpendicular to the radius. We don't know that this line is tangent. We're trying to prove it. So we probably want to try to use that second one. So that second one says if a line is perpendicular, which we don't know for sure if the like tangent segment AB is perpendicular to that radius BC or not, but we can find out for sure. And if we find out, that would mean that yes, that AB would be tangent to circle C. So if it's perpendicular, if AB is perpendicular to BC, that would be a right angle, and that would make that triangle ABC a right triangle. So we really just need to prove that that triangle ABC is a right triangle, and we can do so by kind of like checking with Pythagorean theorem and seeing if it works. Because Pythagorean theorem, like a squared plus b squared equals c squared, only works for right triangles. So if we put in our side lengths and it works, it's a right triangle. If they don't work, it's not a right triangle. So Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. So the hypotenuse is always the longest side. It's also across from the right angle. So in this case, the hypotenuse would be AC. So that's 10. So we'll put 10 in for C. And then the two legs, it doesn't matter which is which as far as A or B. So we'll put BC is 6. We'll put that in for A. And then BA or AB is 8, and we'll put that in for B. So we said 6 we were going to put in for A, so this will become 6 squared. Plus, sorry, my 6's always kind of look like B's. So 6 squared, and then plus B squared, which will become 8 squared, so we're putting 8 in for B, and then equals C squared, which we're putting 10 in for C, so 10 squared. And then now we need to square everything. We can't really add anything together until we square it. So like 6 squared is 36. 8 squared is 64. 10 squared is 100. And then now if we add 36 plus 64, that's 100. So we have 100 equals 100, which is a true statement. So like we put the numbers in Pythagorean theorem and they worked. So that confirms that this is a right triangle. And that means that that little angle in there is a right angle. So AB would be perpendicular to BC. And then that takes us back to this converse up here. So if a line is perpendicular, that's what we just proved, to a radius of a circle at any point on the circle, then the line is tangent to the circle. So that's enough to confirm, like, yes, segment AB is tangent to circle C. Okay, Okay, so yes, segment AB is tangent to circle C, and again, we showed it by like confirming that it was perpendicular, the radius and segment AB. We confirmed it was perpendicular by proving that that triangle is a right triangle, because perpendicular lines create right angles, and right triangles have a right angle. Okay, so example 2, segment AB is tangent to circle C at point B. AB is 7, AC is 25, and we want to find the radius of circle C this time. So this time we do know that it's tangent. So when we do know that it's tangent, we can use that first theorem because it starts off with like, if a line is tangent to a circle, so like, yes, we know that for sure. AB is tangent to circle C. Then it's also going to be perpendicular to the radius. So I'm going to zoom way in here. So AB, this little segment right here, is tangent. That means that it's going to be perpendicular to the radius BC. And if it's perpendicular, again, it creates a right angle. So that would mean that we have a right triangle now, because a right triangle just needs that one right angle. So I'm going to go ahead and label the sides that we were given. AB, they said that was 7. So AB is 7. And then AC was 25. So this side right here was 25. And then we're asked to find the radius. I'm just going to label it as R. So if we have a right triangle and we're missing one of the sides, in this case we're missing that radius, we can also use Pythagorean theorem to solve for a missing side, not just confirm that it's a right triangle. So again, Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs, c is the hypotenuse. So remember that the hypotenuse is always the longest side and it's always opposite the right angle. So the hypotenuse is going to be 25. We'll put that in for C. The 7 is a leg, so it can go in for A or B. And then we're trying to find the radius, which is the other leg. So I'm going to put R in for B, just to kind of like make it match up with the radius. So A is going to be 7 squared plus B is going to be R squared, which we're eventually going to try to solve for. And then equals C squared, which is 25 squared. So now same thing, we have to go ahead and kind of square everything before we start to like isolate R. So 7 squared is 49 plus R squared equals 25 squared is 625. And then our ultimate goal is to solve for R to find the length of the radius of this circle. So in order to solve for R, I'd have to cancel out that 49. It's a positive 49, so I'm going to subtract it from both sides. 49 minus 49 cancels out. I'm going to bring down the R squared. And then 625 minus 49 is 576. And then now I don't just want R squared, I want regular R. So if I want to get R completely by itself, I have to cancel out the exponent, the 2, the square. So I would have to square root both sides. So when I square root R squared, it would cancel out the exponent and it would leave me with just R. And then the square root of 576 is 24. Technically it would be like positive and negative 24, but we're talking about a length here, a radius, so we wouldn't ever be like a negative length or distance. So our radius is 24. Okay, moving down to 13.2, this one has another new theorem. So this one has to do with two different tangent lines, so starting kind of at the top. If two segments are tangent to a circle and have a common endpoint on the or in the exterior of the circle, outside the circle, then the segments are congruent. So if we use this picture on the right as a reference, you can see there's two segments that look like they're tangent to that circle. So there's AD and then there's BD. They're both tangent because they touch at one point A and the other one at B. So if they're both tangent and they have a common endpoint, in this case the common endpoint is D, common endpoint on the exterior of the circle, then the segments are congruent. So that would mean that like AD is the same distance as BD. They're the same length segment. Okay, so example 1, segment RS and segment RT are tangent to circle O. What is the measure of RS? So we're given that RS, which is this segment right here, is tangent to that circle, and then so is RT, which is this segment right here. And they have that common endpoint on the outside of the circle at point R. So since they're both tangent and they have that common endpoint, that means that each of those segments are the same length as each other. So if we're trying to find the length of the segment, we can kind of create an equation, because you can see that there's an expression that goes along with each segment. There's, like, that's hard to see. There's the negative 2x plus 5 and the 7x plus 23. So if they're both the same length, like we just kind of proved they're both the same length, and we're trying to find the length, we can set those two lengths equal to each other, and then we'll have an equation where we can solve for x. So we're going to take the first one for RS, it's negative 2x plus 5. And then for RT, it's 7x plus 23. So I just took, like, this guy right here, negative 2x plus 5, and I set it equal to that expression, 7x plus 23, because those two segments are congruent to each other, and that means they're the same length, so we can set them equal. And then now we have an equation where we can solve for x. Usually when, like, the x's are on different sides of the equal sign, I like to try to get them together as, like, my first step. So to avoid dealing with negatives, I'm going to go ahead and try to cancel out this negative 2x first. So in order to do that, the opposite of, like, negative 2x would be a positive 2x. I'm going to add 2x to both sides. On the right side of the equal sign, I'm going to line it up under the 7x, since those are the like terms. So negative 2x plus 2x cancels out. I'm going to bring down the 5, and then 7x plus 2x is 9x plus 23. I'm trying to solve for x, which means I'm trying to get x by itself. So now that I have all the x's, like, on one side of the equal sign, I just kind of want to move things away from x now. So we have a 9 that's being multiplied by the x and a 23 that's being added to it. Usually we undo addition or subtraction first, so I would subtract 23 from both sides to cancel out that 23 that's being added. So 5 minus 23 is negative 18. Equals, I'm going to bring down the 9x, and then 23 minus 23 cancels out. And still trying to get x by itself, but now I just have a 9 that's being multiplied by x. So the opposite of multiplying by 9 is dividing by 9. So I'm going to divide both sides by 9. So negative 18 divided by 9 is negative 2. And then 9 divided by 9 cancels out, or just 1 or 1x. So we end up with x equals negative 2. But we have to be really careful with these problems, because they're pretty easy to, like, kind of think that you're done when you're not quite done. Because this problem, it asks what is the measure of segment RS, and x is not the measure of segment RS. And you can especially tell because x is negative. So it would make no sense to have a negative distance. So there must be something else that we need to do. So RS, that expression is right here, negative 2x plus 5. So segment RS, it equals negative 2x plus 5. And now we know what x is. I can just take that negative 2 that I just got for x, and I can put it into that expression. So negative 2, and then instead of times x, it'll be times another negative 2 will go in there, plus 5, and then equals negative 2 times negative 2. A negative times a negative is a positive, so it'd be a positive 4 plus 5. And then 4 plus 5 is 9. So that means the length of segment RS equals 9. If for whatever reason, like, I don't know, let's say you just didn't like the expression for RS, like the negative 2x plus 5, we technically could have used either of the expressions, like either negative 2x plus 5 or 7x plus 23 to find, like, what the length of RS is, because the two segments are the same length. So if we find one, we automatically have the other.